Hello everyone, Rowdy here. I decided I'm going to be a good Samaritan to rest the logic world, and I'm going to create a logic processor which allows you to print to a message block by just writing to a memory cell. Now, now of course, this doesn't have to be a normal memory cell, it could just be a memory bank. That's exactly what I'm going to do actually. The processor is going to read from it, and it's going to write to memory cell. So let's get to the text editor to figure out how we're going to do it. So here's what I figured out. First, we're going to need to read the memory bank, obviously, otherwise we wouldn't be able to do anything. But there's two ways to do that, and then you have to parse the input, and there's several ways to do that, and I only see two ways out of there. And of course, you then print the text and then loop forward. So let's actually start writing some code. It's going to be pseudocode, so don't count much on it. First, so I'm actually not gonna do that in a text editor. I'm not too well versed in that. So first, we need to read the memory cell, obviously, and this is going to be our buffer input because we're going to be using this asynchronously. And let's say that the first number is going to mean this is how much the processor is written. So supplied input. We're also going to read how much we read. So read input, and we're going to set that to memory address 1. Now we're going to need to figure out how the hell we're going to print our text. And for me, I think it's quite obvious that we need to have some kind of buffer condition there. Because if you use null as a terminator, then you can't print it. And Linux terminals, for example, can print null. And many other terminals can also print null. So why not just use a buffer condition instead, so that if the buffer overflows, well, we print the text automatically. This will also allow the processor to hard interrupt, I guess, because then you can instantly print, and well, we just have to see it for ourselves. So we have our supplied input and we have a read input. Now what we need to do is we need to check if it's larger than, if read input is larger or equal to 200 and, no, is larger or equal to 512, because if it's 512 or higher, we obviously know memory cells like that don't exist, so we can just continue, I guess. And interesting. So I also thought of another thing. Once we actually read the input, we have no other choice but to clear the buffer. Well, we don't really have to do that, but it would be nice if we could just... It could be nice if we could just go back to our buffer and start over again. Actually, I'm gonna take less than that. So what we're gonna do is we're gonna print flush to message 1. That's obvious, and then we're gonna set both read input and supplied input to 0. Now keep in mind those are pointers, basically. So once we have these two done with, we need to actually parse the input. And parsing input is actually way easier than you think it is. If supplied input is equal to read input, we could just stop reading. So if supplied input is equal to read input, we just go back, because we don't have to do anything, and it can just proceed. Next, we're gonna need to parse the input, and keep in mind we have most of the buffer logic already in place. So what we're gonna do is we're gonna read actually, this causes quite an interesting conundrum. Should we put the buffer metadata at the beginning or at the end? Because if we put it at the beginning, then it's going to cause lots of problems in the future. And that's quite a big issue. But if we put it at the end, then we can read it as metadata. As far as I know, the 6502 does exactly that when it reads from ROM. So I'm actually gonna raise this, and I'm gonna lower this to 510. And now we need to actually do the logic. So we read our characters from bank 1 at whatever we actually read. So at read input. So now this means we can increment read input because we've already parsed it. Now keep in mind it's all safe, we can't actually go over. So read input is going to be equal to read input plus 1. And there we go, we now have all the buffer logic in place. We can just check that. Now we need to actually parse the input. We still have two undefined conditions here, but we already have a buffer condition, so I think we can remove this. And then actually execute it. So now we have our characters. What are we gonna do? Now we might use bit packing, but as you guys know, bit packing isn't exactly good. I would say I would even say it's overkill for something like this. In fact, I don't even think that bit packing is gonna solve our problems, because keep in mind that the maximum a message block can print is 220 characters, which is, I think, around the Twitter message basically. And 220 characters, yikes. We can definitely fit that in the memory cell, but in a memory bank, yeah, I'm gonna make multiple versions of the program here, but of course, I'm gonna assume that we're not gonna bitpack at all. So now let's figure out how we're gonna even do it. So first we're gonna need to figure out how we're gonna read the character, and the best way to do that, I think, is a compile array. So let's set offset to @counter, actually no, to chars times 2. Now keep in mind, chars has to be less than 250, less than 256 for it to work. So I think clamping it might be the best idea here. But you know what? Let's assume that the programmer knows what they're doing, and they can change the code in the future to maybe support another encoding. So now that we have the offset, we can just add it. So we take our counter, and it's going to be equal to counter plus 1 plus chars. Sorry, not chars, to offset. And immediately after, we can start adding our print sequences and callbacks. This is actually a really interesting case because this is null, basically. Then you have to jump somewhere. Where to? Now, we could jump to we could jump to the beginning of the program, so we could start reading another character, but maybe want to do some more processing first. I'm not sure if we're gonna need to do that, but let's continue. Now, I actually prepared for this. I actually wrote some Python code to figure out all the characters we're gonna print. And the camera doesn't seem to be doing a very good job of it, so let me just increase the size. And you can see that there's every single character encoded as Windows 1252. Now, we might be thinking, why did I choose Windows 1252? Why can't you choose UTF-8 for fuck's sake? And the reason is you can't have all these characters UTF-8 has. You can only have a certain amount. In fact, I did the math. You can only have 498 potential characters, which isn't a lot, but considering you have all this space in the code, a whole 1,000 characters, we can just continue. Right, so I also replaced some unknown characters with replacement symbols. That's what UFFFD means. And it's hex 81. It's these three characters, and it's the character back to, and it's the character before J. And of course, there's also XAD, and we're going to be replacing all of these with mindustry characters because, well, Windows 1252 didn't define anything, and mindustry characters would be good for bitmaps and stuff. Right, back to mindustry. Now, there's no way I'm going to be able to do all this alone, so I'll be back with you once I've written all of the code for every single character. So now we have all of our characters inside of a list, and I'm going to be going through each and every one of these characters, and not manually, of course. I'm going to be using a macro. But you might notice that the symbols, rather characters 0 through 31 are missing here. And this is intentional. I actually had to look at what caret notation actually is. So according to Wikipedia, we could just use things like characters from to these ranges, and then just continue on forward, just doing things. I don't know why 63 is the thing, but we'll just go with it. So basically, we need to add every single one of these characters after a caret, and that will be our representation of those characters. And of course, there's 32, but let's take a look at what 7f actually is. So 7f is actually a unprintable character, so we need to replace it as well. In fact, I'm going to do that right now. And of course, one thing I forgot to do before I actually pause the video is I need to set this to less than equals. Now, why am I think less than equals is a problem? Well, if I don't set it to less than equals, this means that it's just gonna go forward and forward once you actually reset the buffer. And of course, resetting the buffer is no bueno. So you just set read input to a higher number than supplied input, and it's just instantly gonna crash the system and produce a lot of garbage on the message block, which we don't want. Now, alternatively, here's the thing. We set supplied input and read input to 0. This doesn't actually mean we set the things in the memory bank. We didn't actually set the memory cells to be equal. So let's quickly fix that. Let's write 0 to 510 and 0 to 511. 0, 10, 511. And now that we have all these characters in there, now that we truly have all the characters in there, we need to actually do some processing on them. Because obviously Mlog isn't just going to take this and then print it. No, that's not going to happen. So let's write a shell for our compiled array. So we take every new line and we're going to need to replace it with a new line just to give it some kind of structure, I guess. But before the new line, we're going to need to put a double bracket. Hold on. Should we? Yeah, I guess double bracket. Then we're gonna need to add a new line, and we're gonna need to set counter 0. This way we can actually return to our code once we're done, and we're just gonna type print double bracket right after. And by pressing replace all, we can now take a look at the fruits of our label. Oh my god, it's yellow. All of it's yellow. I can't actually do anything with this. Well, we need to trim off the end because that's the end of the character set. And I need to do the same thing for the beginning. The null character. There we go, nice and black. You might be thinking, well, hold on. We can't print the double bracket, can we? And we can't. So let's take a look. So because our code in mindustry is mostly the same, and it's also secure, we can just place another processor and then try to print a... Oh dear. Yeah, we can't print the character, and it's just the bracket, which is used for strings. And that might be a problem, but you can just always emulate it with 2 apostrophes. Now, we're actually going to do something else. We're going to try to use a new line here, and then try to print the actual character, just escaping it. And by printing it to message 1, we can see that it turned into frog. Why did it turn into frog? Because this turned into frog right after I saved it. I don't know if it's a bug actually, or if just a nuke didn't implement any escaping. Because he did implement escaping of the new line, why can't he just implement something else? So now that we have all this code, we need to find the double. We need to find the find this thing. It has a sequence of three quotation marks, and we're gonna replace it with 2 apostrophes. It looks the same in mindustry, so I hope no one will care. And of course, there's also escape characters, all that shebang. Let's just assume no one notices. And now we need to do the real heavy lifting. And that is to copy this and then put it right before our code. So now we have the compiled array, which is initialized here, and then it goes all the way down to the 500th line. So let's test it. As if I was going to ignore what mindustry actually does when you import characters that aren't supported in its character set. When I press left twice here, I'm going to the beginning of the string. You can see I'm pressing left and it's doing nothing. So what's actually going on here? Let's re-import this code. Actually, no, I don't. Actually, no. It would be smarter if I just make a new file and then print the differences, or rather search for them manually. But you can see that this character went through instead of these characters. So where did we encounter this issue? Well, again, it takes a lot of meticulous searching. Oh my god. One thing with compiled arrays is they're really dumb. You can't easily find them. And it's next to the letter J and U. And here they are. Yes, I guess we can't print those characters. So we need to find something new. We need to find a character which essentially does what the replacement character does, but it's much fancier. Now I wonder, what would this look like? Net server dot label info pop up actually 300000. God damn it. Is it not client? It could be not client. So let's put it on the screen for like 10 seconds, and you can see that there's the black dot following my dart. That's actually an E. And I think that would be pretty good, but it's not good enough. We need a white block. We need something that is completely white in the Ministry character set. And I know just the candidate. Salt. Now, I don't actually have the Salt character on hand. There's many reasons I don't have the Salt character in my clipboard. For example, maybe I don't need to use Salt in my clipboard. Maybe because I just don't go on CSGO often, and you kinda get Salt there. Maybe because I can't even run that game. But what's certain is that you need to replace all of these characters with something replacement worthy. And give me a second, and there we have it. Now I might be thinking, what does this character look like in game? Well, if I go into Ministry and then chat, it's just Salt. It's literally just a shit ton of Salt. And as you can see, it looks pretty good. It's white, and it doesn't have any of those blue tones like Ice does. So I think now we are truly ready to copy this into the Ministry processor. Ladies and gents, we've done it. We've made the most useless thing ever. And what better way to test it than to have a processor write into it? So let's do just that. Let's set I to 0 and increment I all the time. However, if I is equal to 256, we're just gonna. However, we're only gonna do that if I is less than 256. Otherwise, we just jump back to the beginning. No, that's not what I want to do. Now we just write I to I, as weird as that might sound, and let's go. Bank one, sorry, not sell one. And if we scroll all the way down, we can see that all these were printed in. And we don't actually need this processor anymore now that we did. Now just need to toggle it and set supplied input, which, hold on, what was supplied input again? 510? I could have sworn it was 510. It was. Let's set the supplied input to 510 Just kidding, 256. Screw you. Right. 255 to 510. I didn't see anything because I forgot to put bank 1 in there. Now supplied input is 255 and read input is 0. What's the problem? Well, when we read that, well, let's debug it. Where's the counter? The counter's at 0. Yikes. Of course. I'm a fool. I need to set this to bank 1 as well. But this is strange. If read input is 1 and counter 0, shouldn't it be ticking down a lot? I think I've noticed a pickle. It's going through all of these without actually setting the counter. So it would be wise if I replace space counter with space at counter. Replace all that and put it back in. And it's still not writing anything? I have an idea why it doesn't write anything. It doesn't actually write anything to 511, it just continues. So it has kind of volatile, so now what we have to do is read input to 511, and just like that, we have done absolutely nothing. Why not? Well, I think, well, let's actually replace the processor. Link it, put the code in. Read input is less than 510, that's alright. Supplied input is less than or equal to read input. That's also fine. But if supplied input is more than read input, then we have to go through here and read the characters. Then we increment read input. Yeah, this should be working in theory. But I'm still not reading anything. And the logic debugger says it's switching between read input 0 and read input 1. And it still has cell 1 and all that, so... But we never actually execute this code, do we? We don't. What now? Well, there's another alternative. We could replace the code, but we're gonna need to turn this off. And we still don't see the input from LDB. It's still doing the same flickery thing. So it makes me wonder, have I misspelled supplied input anywhere? Because if I have, then then it would make sense why it resets to 0 all the time. This is all bizarre. And restarting the processor doesn't work. Well, let's do the same thing as we did with that other processor. Read input 1. We can't see written input. Yeah, I'm just gonna skip all the debugging. Found a problem. I wasn't actually writing to bank 1 in the first place, so it printed a lot of null characters into the buffer, and now it's actually increasing. But we're not gonna wait for... Well, it would be better if we can just overdrive this thing, so let's do just that. Silicon phase, and it's already done. God damn it, that overdrive did nothing. But now we can do something really clever. Now we can set... Now I can write 512 to 511, and then watch this. You know how jump functions tend to do really weird things? Well, I'm gonna do something really cursed. I'm gonna import this code, and now this jump function is jumping to itself. That did nothing. Maybe because it did bank 1, maybe because it's cell 1, not bank 1. And we see a lot of null characters. That's all well and good. But now we can just unlink this. Do the same thing as before. Copy this code. Print that code. 255 and 510. And it's reading. It's done. Now we can remove this. Link this to bank 1. It still has all that stuff in it. So let me just put a hash. And ladies and gentlemen, we have printed the Windows 1252 char set. I'm gonna link the schematic in the description, but this is the real issue when you're designing things. You have to account for every single use case, every single problem that you might encounter. Basically, don't be afraid to do things. They'll just exist. Hold on. There's something I skipped. Before I'm actually gonna upload this, I need to figure out what new line is. See, the thing about new line is that new line is a specified character, and it's escapable, and you can define it. So let's get back into the shell. Let's see, Python 3. Python 3 code. Now that doesn't actually tell us anything, but let's take the 0th element, and here we can see that its char code is 10. So if I say echo -e /x 0a, we're gonna have a new line, and that's confirmed because now we have 2 new lines here, not 1. So let's make that small change. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Control J. Let's replace that with n, with \n. And this is our final code. I'm gonna save it up. Send it in the schematic, and you guys will have fun with it. So yeah, thanks for watching, and as always, I'll see you next week.